Hey guys, this is JB from Planning Seeds Tutoring. In this video, we'll be talking about Euler's identity. Don't forget to use my referral code JBMon20 to receive 10% off on your next tutoring package. Alright, so before we get into Euler's identity, I did want to mention a thing about irrationals. Irrational numbers, well, remember, an irrational number is just a number that cannot be represented, not a ratio. It cannot be represented by a ratio. So you can't write it down as a fraction. You can't write it down as a decimal, anything. So an example here would be like the square root of 2, pi, all these numbers like these. We also have other numbers like e and phi. Well, this is the natural number, and this is what we call like the golden ratio, which are all examples of different kinds of irrational numbers. The thing about pi and e for that matter and phi at that time, these are examples of transcendental numbers as well. So a transcendental number is just a number that can't be represented through just mere algebra. You don't represent it just through like brute force. Like the square root of 2, that's an algebraic function. You're just taking the square root of 2, and as a result, you're getting an irrational number. It's a transcendental number. It doesn't come through algebra, but rather it just comes as a result of just some things. For example, whenever you're looking at a circle, you take the diameter of you're comparing the ratio between the circumference and the diameter, and that's how you get the number pi. Well, that's not exactly like an algebraic formula or anything. And that's what a transcendental number is. It's a number that doesn't come through algebra. Not through algebraic functions, at least. Alright. Now that we got that out of the way, we also have other numbers like the imaginary numbers. Well, an imaginary number is just a number that's not in the real number line. So, I mean, the number pi or number square root of 2, I mean, square root of 2 is between 1 and 2. The number pi is between 3 and 4. I mean, it's about 3.14. The number e, that's like 2.718, ... Well, it's still between 2 and 3. It's still like a number that you can represent. Well, imaginary numbers like I, you can't really represent that anywhere on the number line. And as a result, what mathematicians have resorted to is, instead of representing numbers on a number line, per se, so we normally have, let's say, 3, -1, -2, -3. Well, on this number line, we would have, for example, like pi right about there. You would have like e right about there. Example, like just ... Square root of 2 is going to be like somewhere around here, and just keeps on going because it's like about 1.4 ... Well, the thing is, you don't see I anywhere here. So the solution to this is just making a brand new axis and calling it the imaginary axis, and calling the normal axis that we were used to just the real axis. And now you have an entire number plane. Instead of working with just a number line, now we're working with a number plane. And you still have 0 in the middle at the origin, but now if you go upwards or downwards, you would have the imaginary numbers like positive I, positive 2I, and negative I, negative 2I, ... And this is the thing about the imaginary numbers. Well, the thing is, when it comes to I and pi and e, let's go a little bit deeper into them. So the number I is, recall, it's the square root of -1. Well, regardless of what it is, because it is the square root of -1, I mean, there's no real number that you can think of there's no real definite number that you can think of that's actually the square root of negative 1. It doesn't make sense. Negative 1 squared would be 1. 1 squared would be 1. You can't think of a number that multiplied by itself is negative 1. So mathematicians just define this new number, I, to be that number. So I times itself becomes negative 1. Well, based off of that definition, I squared is equal to negative 1. Well, we also know that any number taken to the power of 0, except for 0 at least, is 1. So I to the power of 0 is 1. Well, any number to the power of 1 is just itself, so I to the power of 1 is just going to be I. So now we have I to the power of 0, I to the power of 1, I squared. Let's try I cubed. Well, I cubed is just I squared times I to the power of 1. Because a to the power of b times a to the power of c is just equal to a to the power of b plus c. And 2 plus 1 is equal to 3. Well, I to the power of 1 is just 1. I squared is just negative 1. Or I to the power of 1 is I, or negative square root of I, and negative square root of negative 1. And I squared is negative 1. Well, this just means that I cubed is just going to equal negative I. Now you're left with I to the fourth. Well, I to the fourth is I squared times I squared. And that's just negative 1 times negative 1. And that's equal to 1. And what you're going to notice is that this pattern just keeps continuing. I to the fifth is just I to the fourth times I. Well, that's just I, because it's 1 times I. And then this pattern just keeps on going. So what you're going to notice is that like 4, 5, 6, 4 I to the power of 4 is going to be the same thing as I to the power of 0, which is going to be the same thing as I to the power of 8, ... And I to the power of 1 is the same thing as I to the power of 5, same thing as I to the power of 9, ... I squared, I6, I to the power of 6, I to the power of 10, they're all the same. I cubed, and I to the power of 7, and I to the power of 11 are all like the same thing. And ... It just keeps repeating. And hence, you're going to be noticing that, like, for example, the powers of I, well, it starts off with I to the power of 0, then goes up to I to the power of 1, goes to negative 1, goes down to negative I, and then goes to 1. And just keeps circling around like a circle. All right. The thing about the other numbers, I mean, we're all quite familiar with the number pi. Pi is just the ratio between the diameter, or between the circumference of a circle and the diameter, and you get pi, which is about 3.14. ... Euler's number, E, is actually defined as the limit as n approaches infinity of 1 plus 1 over n to the power of n. Well, this seems a little confusing right now, but if you think about this, actually might seem similar to something that you've probably seen a lot before, and that's compound interest. So if you remember from compound interest, you would be using A as P times 1 plus 1 over n to the power of nt, where n represented like the number of times the value has been compounded. P represents, or this is actually not 1, that's an r over n. P represents, for example, like what the principal interest was, or what the principal amount that you started with was. A is what you end off with. T is how the number of years or whatever time period it is, ... And the R is the rate at which it's being increased. Well, E kind of falls in very similar to this equation. Let's say that you started off with exactly $1 in your account, and you're going to this bank where they're actually doubling whatever it is that you started off with. Well, whenever you're doubling, that means that the rate is actually going to be 100% of whatever you started off with, not 4%, not 10%, ... It's 100%. So you start off with a rate of 1, or 100%. Well, N just represents the number of times it's being compounded. And that's what's represented by A, or that's what A equals. Well, let's say that you're doing this for exactly 1 year. So now you know what T is. That's just equal to 1. And now let's actually give a value for N. Let's say that N is 1. What does this mean? Well, this means that the value, or the amount, it's being compounded exactly once per year, or per the entire amount of time it's being tested, or that's just 1 year. So all in all, the amount of money that you put in, it gets compounded once in that entire cycle. Hence, you're going to be getting 1 times 1 plus 1 to the power of 1, which is equal to 2. Well, that means you put in $1 and then you're getting off $2 at the end of the month, or which is a profit of $1. Not bad, but we can actually do better if we compound it twice instead. If we compound it twice, we would be getting 1 plus 1 over, well, now N would equal 2. If we do it like semesterly or something. 2 to the power of T, well, or not, 1 over 2 to the power of 2 times T, where T is just equal to 1. 1 year. Well, this just becomes 1 times 1 plus 1/2 to the power of 2. Well, that's just 1.5 squared, which is 2.25. Not bad. That's a 25%. That's a 25-cent increase. It's a 25-cent profit. It's even better. Well, we can actually do even better. I mean, instead of doing it semesterly, we can do it monthly or something. If we do it monthly, we'd be getting A equals 1 times 1 plus 1 over 12. 12t. 12 times 1. When you do this, you get a number that's about 2.613. That's $2.61. I mean, that's almost like a 40% increase from last time. That's pretty good. However, this increase doesn't keep on going. If you go up to 365, if you try to do this, for example, every second or every day, or every day and every minute, every second, you're going to notice that the rate at which it's increasing is not changing by too much. In fact, as you approach doing it an infinite amount of times, so not per second, but rather for every infinitesimal time, like a piece of time, like for smaller than a moment, the value that you're going to be getting is about 2.718 So this is just N is just equal to infinity. Whenever we say limit as N approaches infinity, that just means that you're kind of asking what's going to happen when this value N gets very, very close to infinity. Well, infinity is an actual number, so we can't really test it exactly at infinity. So we're just trying to say, well, what happens when it does get near infinity? And that's how we define it. And that's how we define it to be $2.70 or 2.718. This is what we call the natural number. In fact, E is actually used in a variety of different scenarios other than compound interest. Like, for example, the rate at which something damps off due to like friction and stuff. All right, so those are the two rational numbers and the imaginary numbers. Well, okay, how does all this combine together? Well, actually, to get to that, we still need to go around on this complex plane right here. Let's select a point on this complex plane. Actually, I'm just going to draw it up right here. Let's think about a point right about here. Well, we would define this point as, well, just based off like rectangular coordinates, we would kind of call it like 2, 2i. Well, based off like how we kind of define an xy coordinate system and stuff. Well, this isn't exactly a coordinate system. It's actually a number plane. So instead of defining it with like a parentheses and commas and stuff, or as a coordinate, we actually define it as an actual number. We call it as 2 plus 2i. Because it's exactly at 2. And 2i. That's the intersection point. And this is what we call a complex number. Two plus 2i. Well, if you notice the way that I drew it, you would have noticed that I kind of drew it as a rectangle. And this is one of the reasons as to why we call it a rectangular coordinate. Because the fact is, you can draw the point that you're looking at as a rectangle. Let's look at this point right here, at 3 and 2i. This point would be defined as 3 plus 2i. Well, you don't necessarily have to draw it using a rectangle. You could have used any other shape. Let's instead use like a triangle or something. If you use a triangle, and you know whatever this length is, for example, well, how can we define all of these lengths? And that could define, like, for example, your x and y coordinates. Well, this, if you recall, is the opposite. If this is like a right angle, this is the opposite. This would be the hypotenuse, and this would be the adjacent. Well, if you recall, the opposite over the adjacent, or the opposite over hypotenuse would represent what the sine value is, and that's the y value. Equals sine of whatever this angle is. Let's call this angle theta. And the adjacent over hypotenuse would represent what the cosine value is. And using polar coordinates and stuff, or like a polar coordinate system, which you guys can actually look through in like one of my previous videos, you can notice that, well, this could represent the y value and this could represent the x value for a standard coordinate plane. Well, that means that you can kind of represent every single coordinate here as, instead of a value in terms of like the the real number and the, where was it? Instead of representing each of these numbers in terms of the real numbers and the imaginary numbers, you could have instead represented it as, in a slightly more complex way at least, as something like whatever the theta is. So sine theta times whatever this hypotenuse is, I guess, whatever the length is. Well, that's actually going to just be 2i. And cosine theta, well, h times cosine theta, that's actually just going to be 3. And together that defines this point. All right. Let's take a small step backwards here. The thing about sines and cosines is they're a little difficult to work around with. I mean, it's a ratio to begin with, and if you look at, like, for example, a graph of it, it's not exactly ideal. Well, the thing is, both sine and cosine, these can be represented or approximated using a polynomial function. You can approximate it using polynomial functions. And these are a lot nicer. These are significantly nicer because you can easily take the derivative of polynomials. Well, if we take the derivative, the way that we kind of actually approximate sines and cosine, it's through a process known as the Taylor expansion or the Taylor polynomial expansion. And what this tells us is, well, what this person Taylor, what he noticed is that when you're trying to define a certain function, like sine, in this case cosine of x, he noticed that you could take this formula right here as So what this just tells us right here is this is the actual fact that he kind of noticed. He kept adding whatever like an initial point of a problem was, and then he just kept adding the derivative from that point, and what he noticed was that he was able to kind of approximate what each of these like functions were. Well, this x minus a portion, this just represents like where he kind of started off with. And a few things that he noticed was were the fact that the approximation, the polynomial approximation, is very, very good at the place that he started off with, at point A, or wherever he centered it around. But it gets significantly harder, or it gets significantly more limited, or it gets a lot worse when you go further out. So what I mean by this is, for example, if you look at this cosine function right here, if you zoom in very, very deep, well, this looks like at least right about here. If you zoom in very, very close to 0, it looks like it's just a line that's just like y equals 1. It looks very close to it, at least. But the more you zoom out of it, you notice that that's not exactly the case. But what Taylor did, he instead started using the derivative. He started using the derivative after every single term, and what he noticed was at every single point, after he kept adding more and more derivatives, it kept getting closer and closer to the approximated value. So an example here would be, I can use, for example, this is the line cosine of x, and now I'll turn on the line y equals 1. Well, y equals 1 and y equals cosine of x, at least right about here, seem to be fine. But sooner or later, you notice that they kind of, well, very soon, they seem to get out of hand. Well, next what he did was, he instead of using just 1, he used 1 and then the derivative of cosine at least. Well, that seemed to be significantly better. They're both blue, at least in this one, but you can kind of see that, at least for a while, the minus x squared over 2 is pretty close. Well, once he did it for one more time, he added another, he kept adding more and more derivatives. Well, he just added a derivative once again, and what he noticed was this is even closer. It kept getting closer as he added more and more derivatives. In fact, as you approach this number, as you increase this number significantly, you kind of get to see that it gets closer and closer to like the exact value of sine. All right. So what Taylor was able to do was that he was just able to make a function for all of a polynomial kind of expansion for all of these different functions, or for sines, cosines, the e to the power of x, the exponential function, amongst a variety of other functions. He defined sine of x, or not him, rather Maclaurin. A Maclaurin series is just a function where this a value right here, it's equal to 0. So that's what a Maclaurin series is. So Maclaurin series, the Maclaurin series of sine of x is just x minus x cubed over 3 factorial plus x to the 5th or factorial minus x to the power of 7 over 7 factorial. And cosine of x, and this keeps on going, this pattern just keeps on going. Cosine of x is just equal to 1 minus x squared over 2 factorial plus, he kept taking derivatives and he just kept going, plus 4 x to the power of 4 or 4 factorial minus x to the power of 6 over 6 factorial, and this kept on going. He kept doing this for infinity, and this is very, very, like, almost identical. This is identical to what sine of x is and what cosine of x is. But he also noticed that e to the power of x is actually just equal to 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus dot 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 dot. Well, we kind of defined these points right here as cosine of x plus I times the sine of x right here. Well, if we try using the Maclaurin series right here, using the definitions from here, what you're going to notice is cosine of x plus I times the sine of x. Well, if you plug in an I times sine of x right here, we're just plugging in I for every single term. All right, and now you get cosine of x, well, 1 minus everything from right about here, and you're just adding all these terms right here. Well, when you add up all these terms, you're going to notice that 1 plus ix minus x squared over 2 factorial plus, or rather minus ix cubed over 3 factorial plus x to the 4th over 4 factorial plus I times x to the 5th over 5 factorial, and this just keeps on going. Next would be like a minus x to the 6th over 6 factorial dot dot dot. And this would be, well, whatever I times sine of x plus cosine of x is. Well, if we actually just take out an e, or if we just take out an I right about here, we just say that I is just taken out or something. Or actually, instead of taking it out, let's actually just like keep it with the x kind of. What you're going to notice is that you can re-represent this as 1 plus ix plus I squared, or I times x squared over 2 factorial. Instead of letting x, the value right here that we're looking at, instead of just being like x or something, let's say that it's equal to I times x. And what you're going to notice is that this is just equal to ix cubed over 3 factorial plus I x to the 4th. By the way, this value right here was I x to the power of 0, and that's why we got 1. Over 4 factorial plus I x to the 5th over 5 factorial dot 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 dot. Well, what you're going to notice is, well, this equation right here, it's very, very similar to the e to the power of x. Well, in fact, if instead of using e to the power of x, instead of using x, if we used e to the power of ix, this is exactly what you would have gotten, which is equal to I times sine of x plus cosine of x. So you just got e to the power of ix is just equal to cosine of x plus I times sine of x. Well, if you use, instead of using x, let's use like an actual angle instead. Let's actually define it using angles. I theta equals cosine theta plus I times sine theta. If you actually plug in a value of theta, for example, a theta value of pi, so e to the power of I pi, well, that's just equal to cosine of pi plus I times the sine of pi. Well, this just comes down to recognizing your unit circle. Sine of pi is equal to 0. I times 0 just becomes 0. Cosine of pi, well, that's equal to negative 1. And what we get is e to the power of I pi is equal to negative 1. Or in other words, if I bring this 1 over to the other side, I get e to the power of I pi equal to, or get e to the power of I pi plus 1 equals 0. And this is a fascinating identity because you have three numbers, or actually 5 different numbers, that are related to one another here. You have two transcendental irrational numbers that's also just like combined with an imaginary number, a number that does not exist at all. And you're adding like two very common numbers, two just very, very plain, like just normal numbers, I guess. And you're getting an actual value. You're combining it all together and you're getting an actual just normal value. And this is what almost every single mathematician considers this to be the most beautiful identity of all times, or identity or equation possible. That's e to the I pi plus 1 equals 0, and that is Euler's identity. Alright, I hope you guys learned something from this video, and this just shows to show how broad math is overall. And even though this math right here doesn't seem very useful in terms, but it just shows you how broad it is in sense of a variety of different reasons. In fact, this identity does get used in like further theories in like string theory and stuff, but that's for another reason. Alright, thanks for watching. I hope you guys learned something.